the concept of infimum and supremum. This is a very important concept, and we should treat it as such. Now, infimum of a set, let me just put down notations. If E, suppose E is given to be a non-empty set. We assume E is a non-empty set. And we assume that E is bounded below. If E is bounded below, it means that E has a lower bound. And if it has a lower bound, then it has infinitely many lower bounds. And therefore, there must be one that is greatest than the other lower bound that is greater than all the other lower bounds. That lower bound that is greater than all the other lower bounds is what we call the greatest lower bound. Lower bound of greatest lower bound of E. Greatest lower bound of E. And this greatest lower bound of E is also called the infimum of E. The greatest lower bound of E is abbreviated GLB of E, while the infimum is abbreviated INF of E. So these are the notations we should use. But both of them are the same, but we'll use them interchangeably. Preferably, I'll be making use of INF of E. Now, if E is as given a non-empty set, if we assume that E is bounded above, then the least upper bound exists. Once a set is bounded above, the least upper bound exists. That is, the least of all the upper bounds exist. Once a set is bounded below, then the greatest of all the lower bounds exists. That greatest of all the lower bounds will be called GLB of E, or the infimum of E, inf of E. If E is bounded above, then the least upper bound, the least upper bound of E is also called the supremum of E. And here, the least upper bound of E is abbreviated LUB of E, and this is also taken to be sup of E, where the supremum of E is abbreviated sup of E. These two are the same thing. They are identical. Now, let me point out here immediately that a set that is not bounded below, if a set is not bounded below, there is nothing like the greatest lower bound. Well, I'll throw more light on that. Because for a set that is not bounded below, we may conventionally call its greatest lower bound minus infinity. And the one that is not bounded above, which I call its least upper bound, that is the supremum, plus infinity. So when we get to that point, I'll throw more light on that. So now, what I want us to do is to look at the concept of infimum and the supremum and see how they are characterized. So, let us look at the characterization inf for infimum and sup for supremum. Now let us see how we characterize them. Let E be a non-empty. A non-empty A subset of R, such that E is bounded below. If E is bounded below, then a lower bound exists, and once a lower bound exists, there are infinitely many lower bounds, and therefore the greatest of all the lower bounds also exists. So for a set to have the greatest lower bound, that set must first of all be bounded below. So then alpha naught, or rather let me say theta naught, equals infimum of E if and only if, this is how we know that the least upper bound of E, if and only if I, for any x in E, theta naught is less or equal to x. That is to say that theta naught is a lower bound. That is theta naught is a lower bound. Is a lower bound. So the first thing that should be satisfied is that theta naught is a lower bound. Number II, if for any x in E, theta is less than or equal to x, then theta is less than or equal to theta naught. What this means is that for us to talk about the infimum, which is the greatest lower bound, that greatest lower bound, of course, by definition, must first of all be a lower bound, because the greatest is a lower bound that is greater than every other lower bound. So it must be a lower bound. And not only that, if there is any other lower bound, this is the one that makes it the greatest. If you establish another lower bound theta, then that theta must be less than or equal to theta naught, meaning that the theta naught is the greatest of all other lower bounds. Is the greatest of all lower bounds. Let us take this, for instance, as an example. Consider the set, say E equals 1, 2, 3, and 4. Let us look at this set. I want us to observe that for any x in E, 1 is less or equal to x. Let me put here as I. For any x in E, 1 is less or equal to x. And II, if for any x in E, theta is less or equal to x, then theta is less or equal to 1. This is true. Of course, 1 is less or equal to x because from what we are seeing, 1 belongs to E. And 1 is smaller than every other thing in the set. And also smaller than or equal to itself. So, or is equal to itself. So 1 is smaller or equal to everything in the set. That's what gives us the first one. Now, if for any x in E we have that theta is less or equal to x, then in particular theta will be less or equal to 1 because 1 is one of these x in E. So this means therefore, by the characterization we give above, we have that 1 is equal to the infimum of the set E, where E is defined as, where in this case E is equal to the set 1, 2, 3, and 4. E is equal to the set 1, 2, 3, 1, 2, 3, 4. So 1 is the infimum because 1 satisfies the condition of the definition we gave above. Next, another interesting characterization of the infimum of a set E is the following. I will say alternatively. But theta naught equals infimum of E if and only if. I'll put here I with prime. If and only if I prime for any x in E, theta naught is less or equal to x. Then I prime for any epsilon bigger than 0. Epsilon bigger than 0 means given any positive number. Given any positive number, theta naught plus that positive number is not a lower bound. Is not a lower bound. So what this means is that once theta naught is the infimum, that is the greatest lower bound, it must be a lower bound. And for the fact that it's a lower bound, the greatest of all the lower bounds, if you add a positive piece to it, the new number you will get will no longer be a lower bound. And the reason is because this is what? The greatest of all the lower bounds. And what this means pictorially is the following. If I have this, assuming that this is the set E, as I said, remember that E is not necessarily an interval. And here we have that this point is theta naught. Theta naught is being the infimum, means that what? Theta naught is the greatest of all the lower bounds and is at the same time a lower bound of the set. Meaning that if you pick any x in the set, that x must be greater or equal to theta naught, or rather that theta naught is less or equal to x. But the second condition, this place is telling us that once you give me a positive number, any positive number, once you give me any positive number, then adding it to theta naught will move us to the right. And if it moves us to the right, it means that we'll come to somewhere here, theta naught plus epsilon. So when you get to theta naught plus epsilon is no longer a lower bound. What this means is that theta naught plus epsilon not being a lower bound means that there is something in the set that must be smaller than theta naught plus epsilon. Otherwise, theta naught plus epsilon will be smaller than everything in the set. And if theta naught plus epsilon is smaller than everything in the set, it contradicts the fact that theta naught is the greatest lower bound. Because in this case, we have something that is bigger than theta naught that is still a lower bound. So theta naught plus epsilon is no longer qualified to be a lower bound. That is what we are saying. Now, to paint a better picture of this, I'll still put alternatively. Theta naught equals infimum of E if and only if, I'll put I prime prime, for any x we pick in E, theta naught is less or equal to x. And I prime prime, for any epsilon bigger than 0, for any positive number you give me, there exists x depending on epsilon in the set E. There exists x depending on epsilon element of the set E such that theta naught is less or equal to x epsilon, and this x epsilon is really less than theta naught plus epsilon. This actually brings out the true picture of what we mean in the second characterization, in this alternative, that theta naught plus epsilon is not what? Is not a lower bound. Now, what does this mean? What this is telling us is the following. Let us maybe see if we can visualize this through this picture. Here is the set. Somewhere here is the set. I assume here to be the set E. Here is the set E. And the theta naught. Theta naught is a lower bound. Theta naught is the infimum. What makes it different from the other lower bounds is that, assuming that maybe somebody stands here, let me assume that there is a person here, and that person stretches the leg to the right, and that person covers a distance epsilon greater than 0. That epsilon, for the fact that the person covered a distance epsilon, where the leg will land on the line will be theta naught plus epsilon. Now, what we are saying is that that person must have in between his or her legs a certain element of the set, which are called x epsilon. And of course, the x epsilon depends on epsilon, because the length of epsilon, that is, depending on how small or how large epsilon is, will determine the position of X epsilon. But there must be one that is a member of E which satisfies this. That is what we mean by theta naught plus epsilon no longer being what? A lower bound. This particular inequality is very, very important and must be remembered as it appears. This less or equal to here is very important, and this strictly less than must be maintained this way. So these are the characterizations of, we've given about three equivalent characterizations of what it means for a number theta naught to be the infimum of a set. The problem to be, that is when we start solving problems. The problems to be solved will determine, the nature of the problem will determine which of the characterizations that should be used. And there is another characterization which is very, very important and must be touched. But unfortunately, I cannot do it now, but I will mention it. Unfortunately, I cannot do it now, but I will mention it in the sense that the gadgets that I will need to really throw a very good light on it is not yet defined. And that gadget is the gadget of, that is the sequence, definition of the sequence of real numbers. Now, what I want to point out, and let's just mention it. When we get there, when we talk about the sequence of real numbers, I'll try to recall what I've said. And that is the following. That whenever theta naught is the infimum of a set, that is whenever we're given E and the E is bounded above, meaning that the infimum exists. If theta naught is that infimum, then there is a sequence in E that converges to theta naught. You see, this is why I say I should mention it without doing more on that, because I've not discussed what a sequence is, and I've not discussed what convergence is. So for the fact that I have not done this, I'll reserve it until I introduce sequence of real numbers, talk about convergent sequences of real numbers. After that, we'll bring in this notion that whenever we have a subset of E that is bounded below, then the infimum exists, and there is a sequence in that particular set that converges to the infimum. Let us just bear this in mind. Now, what I will now do is, having done these characterizations, and if you see, you'll find out that as we are going on, I decided to continue with infimum only, reserving discussion on supremum. What I intend to do is that I will end this lecture with a discussion on infimum, hoping that a follow-up lecture, I will now talk about the concept of supremum and also give this kind of elaboration, because the same kind of argument will lead us into getting various characterizations for the supremum of a subset of R when such exists. Now, for us to complete today's this lecture, let me give some examples. I want us to look at the following. Given that let E be equal to, say, the interval, the open interval AB, which is equal to the interval AB. When I write this open interval AB, now it's good that I'm bringing this up now. Remember, when I introduced this interval, I underlined the word open and underlined the word bounded. Remember then I call this interval an open bounded interval. Here, having discussed bounded sets, the boundedness in the definition of this interval comes from the fact that this interval is bounded below by A and bounded above by B. It's bounded below by A and every number smaller than A, bounded above by B and every other number bigger than B. This means that since this particular set is bounded below and bounded above, then it is what? Bounded. That is where the bounded we saw in its name came from, because it's a bounded set. That being open, that is calling open, the word open, I will not say more on it, because it's what we can call in quote topological concept. That one will be reserved when we get to a stage where we bring in the meaning of a set being open. we shall again see that when that is done, that this interval in R will turn out to be an open set. And it's from there that that open in the name came from, because it will turn out to be an open set. Here we've seen that it's a bounded set, because it is bounded both below and what? Above. Good. Now, what do I want to do? What I want to do here is, we are given this interval. Please let us note that, as I mentioned when we introduced these intervals, I'll be using these notations interchangeably for now. Be using any of them. So when I write, which I believe we will understand, we'll go back to see what each notation represents. Now, I want us to compute. Of course, we've seen that by definition, E is equal to the collection of all x in R, so that A is less than x less than B. A is less than x less than B. Meaning that, remember pictorially, we have this, assuming that somewhere here is A and somewhere here is B. Remember, A is not a member and B is not a member. We are talking about all points that lie between A and B. What is this example? What does this example require us to do? What I want us to do is to prove that the infimum of this set E, that is the infimum of the interval AB, is equal to A. The infimum is A. Now, remember, I can talk about the infimum because we've already seen that any x here is bigger than A, meaning that this set is bounded below by A. It's also bounded above by B, meaning that the set in question is bounded because it's bounded both below and above. But interestingly, the lower bound, which is A, this A as a lower bound is not a member of the set. This B as an upper bound is not a member of the set. And that is why the definition of being bounded below and above will require that that particular number exists in R, not necessarily in the set. So let us try to see if we can prove that infimum of A is equal to A. It's more A. Infimum of E is equal to A. So how do we go? The proof goes thus. Proof. Observe that for any x we pick in the interval AB, A is less than, I can say A is less than or equal to x. In fact, A is less than x. A is less than x. Thus, A is a lower bound of E equals AB. So A is a lower bound. Next, number II, let epsilon bigger than 0 be given. That is to say, we are given a positive number. Remember, the characterization here says that theta naught is the infimum if and only if for any x in E, theta naught is less than or equal to x. And for any epsilon bigger than 0, there exists x epsilon in E such that theta naught will this inequality will be satisfied. So if I'm able to show that these two inequalities, these two statements hold, then we'll conclude that theta naught is the infimum of the set. So these are the formulas, what I'll call formulas for showing that theta naught is the infimum. So that is what I'll do now. I've already obtained here that A is a lower bound, meaning that I holds. This I holds. So what remains is to get that, given epsilon bigger than 0, I can find x epsilon in E so that this inequality is satisfied. Once I do it for this interval, where in this case our theta naught is A, we conclude that A is the infimum of the set. So let epsilon bigger than 0 be given. Our job is to we find x epsilon in the set AB such that A is less or equal to x epsilon and this x epsilon is less than a plus epsilon. This is what we want to do. So once we're able to find this x epsilon, then we are done. If we're able to find x epsilon that will satisfy this inequality, then it means that A is the infimum of the set. So how do we find this x epsilon? I would like us to look at this interval again. Look at the interval. I want us to observe this. There are two cases. One of the cases is that from here, the epsilon could be this from here to here could be of length epsilon. So that if this is the case, then somewhere here will be A plus epsilon. Somewhere here will be A plus epsilon. Another possibility is that here is E and epsilon runs so large that it goes beyond B. In that particular case, somewhere here it will be, say, A plus epsilon. So what are we saying? Epsilon could be such that it is less or equal to the distance from A to B, or it is bigger than the distance from A to B. Now let me put this down here, even though I've not introduced that notion before. I mentioned it when I talked about absolute value function, but all of a sudden I did not discuss it. If I have given x, y in R, two real numbers, the distance between A and B will be denoted by dxy, and this is nothing but absolute value of x minus y. This absolute value of x minus y is nothing but what we call the length from x to y. So if here is x and here is y, this value gives us the length from here to here. That is what absolute value of x minus y represents. So here from here to here is the, if I do absolute value of A minus B, I'll get the length of this interval. So there's possibility that epsilon given is smaller than the length of this interval, smaller or equal to the length of this interval. There is also a possibility that epsilon given is bigger than the length of the interval. In that particular case, A plus epsilon will fall above B. But in a case where epsilon is smaller or equal to the length of the interval, then what may happen is that either A plus epsilon is less than B, or at worst A plus epsilon is equal to B. So if this is the case, we can now, with the picture I've given, we are looking for x epsilon in AB that will satisfy this inequality. It must be greater or equal to A, but less than A plus epsilon. So how do we make choice of this x epsilon? To choose the x epsilon, we choose it as follows. Choose x epsilon to be equal to, let us look at here. X epsilon should be chosen to be A plus epsilon over 2 if epsilon is less than or equal to the length of AB. If epsilon is less or equal to the distance from A to B. Remember that from here to here is the length of AB, the distance from A to B. And so if we choose this, you'll find out that in that particular case, x epsilon A plus epsilon over 2 will give us somewhere here, A plus epsilon over 2. So if I call this x epsilon, you will see that this x epsilon satisfies what we are looking for, because it lies between A and A plus epsilon. But what about the situation where A plus epsilon is already above B? In that particular case, we do not have trouble, because that is the easiest case. In that case, you observe that if we choose any point x between A and B, we are done. Because any point x between A and B must be such that A is less than or equal to that point x, and that x is really less than a plus epsilon. So we choose a plus epsilon over 2 if epsilon is less than or equal to a minus b. And we shall choose x epsilon to be, say, any x in AB if epsilon is truly greater than the length a minus the length of the distance from A to B. So this is how to make the choice of x epsilon. And with this choice, with this choice of x epsilon, it is easy to see that A is less than, in fact, A is less than or equal to x epsilon, and this is really less than A plus epsilon. So that is it. So with this, we can conclude, therefore, that A is equal to the infimum of the set A, comma B. So A is equal to the infimum of A, comma B. So this is an example. And I intentionally bring this example in now because many people will still find it difficult to follow me, in the sense that it's somehow technical to achieve this. But I brought it in so that by the time I repeat it again, maybe in the next lecture, after the viewers must have gone through this, by the time I repeat it again and throw more light on it, this will now sort of sink, in the sense that more better understanding of it will be made. So for now, that is what it is, that we can make choice of x epsilon in this way. Let me give one more example before I stop. I'll give an easy one. Example. Consider the set x equals 1, 2, say 1, 2, 3. Let us take the set 1, 2, 3. I want us to observe that for any x I pick in X, 1 is less or equal to x, meaning that 1 is a lower bound. I think, yes, 1 is a lower bound. I think I've given something that resembles this before. And also, number II, given epsilon bigger than 0, if we choose x epsilon to be equal to 1 in X, then 1 will be less than or equal to x epsilon, and this x epsilon will be less than 1 plus epsilon, meaning that 1 is a lower bound, and for any epsilon bigger than 0, there exists x epsilon equals 1 itself, so that 1 is less or equal to itself, which is x epsilon, and 1 is really less than 1 plus epsilon. This is a true statement. And this means, therefore, this is another way of saying, therefore, that 1 is equal to the infimum of x. What I want us to see from here is that if we look at the definition we gave at the beginning, the definition of the minimum of a set, we shall see that 1 is the minimum of x, because 1 is in the set, and 1 is less or equal to everything in the set. Here now, with what I've just done here, we see that 1 is the infimum of the set x. So what I want to point out here is that once a set has a minimum, then that minimum automatically becomes the infimum of that set. We shall see a similar thing when we discuss the concept of supremum in full. Once a set has a maximum, then that particular maximum automatically becomes the supremum of that set. The supremum of a set, we remember, is the least upper bound. So we shall see this in our next meeting. Before I conclude this, let me quickly make this remark. And this, I believe, will be helpful to so many of us. Some authors will do this kind of thing. If they want to say that a set is bounded below, say by alpha, they say that a set is bounded below if there exists alpha in R such that alpha is less or equal to x for all x in the set. Say the set is E. This is commonly used. But if you watch what I've been doing, you'll find out that I will rather write that E is bounded below if there exists alpha in R so that for any x in E, alpha is less or equal to x. If you watch all through, this is what I've been doing. But if you read some literature, this is what you will see. Many people have been using this, but I do not think it's correctly placed in the sense that it would create some difficulties, especially when you want to negate this statement. If you want to negate this statement, remember from when we did the universal quantifier and the existential quantifier, we say that we negate this statement if we to negate, we change all existential quantifier to universal quantifier and change all universal quantifier to existential quantifier. But here, to negate this, you'll find that I will be in trouble in the sense that once you change this for all alpha, I don't know, jumping this to come here and change this will be a problem. But if you present it this way, you'll find out that for all alpha, there exists X alpha such that something happens. It's better that we do our expression in this way for negation to be easy than to do it in this form. And I think this is a good place to stop for today. Thank you so much for listening. Hoping to see you soon.